if you remember last class, what we did is we were discussing the chemical potential. Mu is mu star plus R3 x. Now this was for solvent, but we just showed that this can also hold true for solution. In a solution. So star is for the pure solvent, pure solute or pure solvent. Clear? Now the question is, okay, so if you look at these equations, okay, so what we are saying is that the chemical potential, okay, in the ideal case means when the solute of the solvent, okay, is in its pure form, right? That is mu star. And that will be lowered in solution. That's it, right? And this is again using the ideal case in the sense that there are two things. One is, of course, we took the vapor as ideal, right? Because we took the ideal gas equation. Second thing, there was another thing which was ideal. We showed that the variation of the pressure with respect to the mole fraction was a linear. That is also an ideal variation, right? That was basically Raoult's law. We showed it, right? There is a straight line. So if these two are valid, only then these two equations will hold. Clear? Okay. Now all these things actually give rise to something which is known as colligative properties. Now, colligative means actually it came from a Latin word. It's basically means it's together. Okay, and the idea is that it doesn't depend on which solute you use. Okay, like for example, if I add sugar, okay, or say salt in water, it don't matter like how much will be the say chemical potential change, because all these equations show that suppose for water, right? One is water. Now I'm asking how much actually will be the chemical potential of water if I add some amount of salt or some amount of sugar. It doesn't matter because actually it all depends on x1, mole fraction of water. Okay, so if I suppose add, okay, something like sodium chloride or some sugar, okay, as long as the mole fraction of water is same, it is saying that the chemical potential change will be same. Okay, so irrespective of any substance, okay, these properties will be shown, which is of course not an like a real case, right? Because we are assuming that things are behaving ideally, and if it is ideal, everything like will behave ideally. Okay, something like we said, like let's say carbon dioxide and oxygen. If I actually go to very sufficiently low pressure, both behave ideally. So you cannot say that one is behaving like different from the other. Okay, same thing is here. Okay. Now, what are the colligative properties? Already we told you one thing, like the vapor pressure will be lowered. That is one colligative property. Okay. How much amount it will be lowered? We already said that it will be, if P star is the original vapor pressure, right? It will be basically the lowering will be proportional to P star into X, right? It will be proportional to the mole fraction. So the like vapor pressure lowering itself is a colligative property. There are also other colligative properties. One of these is you know already. Freezing point depression and elevation of the boiling point. Okay. Now that can be very well understood, like from this mu versus T curve, which we already discussed. Okay. And if you remember that we need to use different colored chalks. So for example for solid, right? So solid actually mu does not change that much in temperature, right? Which I am not drawing up to here. For liquid, what will happen? We will have something, right? Some slope. We discussed all this, right? For gas, actually it will start from very high level, okay, and the slope will also be very steep. Something like say this, and let's say maybe we get this, okay. And suppose these two lines actually cross. Okay. So the yellow line is for vapor. The blue is for liquid and the red is for solid. Okay. Now the question is, what is my melting point here? Here, right? Freezing point or melting point. And what is my boiling point? It is here. Okay. So I'm just calling it as TF. F stands for freezing point, or you can write it as TM. Okay, and TB for boiling point. Right? Now, suppose this is for a pure substance. Okay. Pure substance in the sense, suppose I have pure water. Okay. Now I am adding some sodium chloride to it. Okay. Now the assumption is that what the sodium chloride is going. The sodium chloride actually is going to the solution, of course, but it won't go into the vapor phase because it's non-volatile, right? So the vapor will always be pure. Okay. But in the liquid phase, when I am adding sodium chloride, I know that the chemical potential should drop, right? Also, we can assume that the solid phase is pure. Like solid phase pure means actually when it is crystallizing, forming solid, you can think that the water is crystallizing separately from the sodium chloride. That's an assumption. Okay. Then we can further assume that the solid curve will also not change. So the only curve, the change for mu that will happen is for the liquid. Clear? Okay. So, and if we also assume that this change is kind of same throughout the range of like temperature, we'll have a curve like this. Right? It is basically lowering. Right? Why lower? Because actually mole fraction is just a fraction, right? And ln(x) will give you a negative value. So we see that like the freezing point is depressed, okay, but the boiling point is actually elevated. Right? So the cross points actually now change. Okay. Basically the solid liquid cross point and the liquid vapor cross point. Because I am only changing the liquid, assuming that the change in chemical potential is happening only in the solution phase. Okay. And when the things are solidifying, okay, the water or the any solvent, okay, that solidifies on its own in its pure form. Okay. Now, which means that I will have a depression in the freezing point, if I just call it as a P prime, and the elevation in the boiling point. But note here that the elevation in the boiling point is smaller than the freezing point depression. Okay. Secondly, we could have actually shown it in the pressure versus temperature curve. Remember that we actually introduced the phase diagram from there. Okay. Now, what is a typical phase diagram? Like for water, say. Okay, water has a slightly negative slope, right? And then it is something like this, right? Now, what I am trying to say here is that suppose this is 1 atmospheric pressure. At constant pressure, this is my boiling point, okay, and this is my freezing point, right? Because this is solid, this is liquid, this is gas or vapor, right? These are the regions. Now, what will happen if I have, if I basically add, okay, as something like say solid, okay. So these two curves will change. Why? Because the liquid is in equilibrium with the gas and the solid. Okay. But the solid all of a sudden will not change. But the liquid gas itself will not change. But the equilibrium lines will shift. Okay. So as a matter of fact, what will happen is that the triple point will come down here. Okay. And you will have something which is parallel to this. Okay. And also which is parallel to this. Clear? Okay. So I'll have basically freezing point depression like this. Okay. And elevation of boiling point like this. Okay. But again, you can see that this will be small shift. Actually, this comes from the slope of this curve. Okay. If it is steep, the shift will be more. Something like that. You can easily see. And this slope is much shallow, right? That's why the shift is basically small. Okay. And overall, the triple point also comes down. Now the question is, can we actually mathematically express it? Okay, so what we want that given the amount of like a salt added. Okay, how I can actually define this quantity, which I am saying something like delta T or dt, or this quantity. Okay, how to write that depression in the melting point or freezing point, okay, or the boiling point, okay, as a function of mole fraction of solute or solvent. Okay. So can you mathematically actually write it? Again, the starting point is the same, and as you can see, the starting point will be like chemical potential of a particular substance. Okay, it's same in every phase when the equilibrium is attained. Okay. All right. So let us proceed. Any question after this one? No. All right. Alright, so let us first consider any one of them. Let's say freezing point depression. Freezing point depression or loading of freezing point. Okay. Now, what should be the approach? Like, again, what is in equilibrium? The liquid is in equilibrium with the solid in this case, right? Now, the solid is pure, but the liquid is a solution. So, the chemical potential of the solvent should be equal in this two medium. That's the starting point. Okay. So, the chemical potential of the solvent, I'm just using the notation I was using. I'm using one notation for the solvent. Okay. In the solution, basically, okay, should be equal to the chemical potential or in the solid. Okay, clear? Now, when I say solid, solid is always in pure form. That is the assumption. Okay, so I can write this thing as mu star. Okay, now chemical potential is what? It gives to energy per unit mole, right? So it's a function of pressure and temperature. Okay, now this guy is not only a function of pressure and temperature but also a function of the mole fraction. Okay, because as we know that this is basically mu star plus RT/LNX. So it is P, E and X1. As simple as that. So you just write it. What is, let me now write the solution thing here. Okay, or maybe I can just write it as, yeah, you can keep it. So mu is nothing but mu star, right? Plus RT ln x1, right? That is equal to the mu1 star in solid. Okay. So again, I'm basically taking the component 1, which is solvent. Now we can just play around. Now you see here. So what we can write it, this entire thing as. So you see, I have solid and this is solution, right? If I write it as a solution minus solid, that's so. Then it's basically tells me the melting process. Okay. So what I'm going to write is something like RT/ln x1. All I am going to do is to get a relation of x1 and that temperature difference. Okay. So RT/ln x1 is, I can write it as mu solid minus mu solution, or maybe actually let us actually use the word liquid. That will be better. Okay. Mu liquid. So mu, I can write it solid minus liquid, but solid minus liquid is what? It's a freezing, final state minus initial state. But I want to write it in the other way because I'm talking about melting. Okay. So I can just write it as a minus mu solid, mu liquid minus mu solid. These are all mu star. Okay. Clear? Okay. So I can write now divide by RT. Now what is this difference? This is the Gibbs free energy per unit mole difference. Okay. For going from solid to liquid. So this is nothing but delta G of melting. Okay, or fusion basically. So just write it as minus delta G. Remember that we are using a notation. We will write the word fusion here because it's the process. Okay, delta fusion of G divided by RT. But this is for one mole because it's a mu. So I am using also the bar notation. Okay, clear? Now again, let's see. So where we are, ln x1. Okay, fine. Now still we do not know actually like what is the delta t kind of relation. Meaning we have to somehow integrate it when say the x is from pure to x1, something like that. Okay, and how the freezing point changes. Because freezing point depression means what? Depression with respect to what? Pure liquid, right? So I have to somehow integrate it eventually. Okay, when x1 is equal to 1, what happens? And when x1 is equal to some arbitrary x1, what happens? Okay, but before that, we'll just pay a trick. The trick is that usually we do not actually measure the delta G. Why? Because when you measure thermodynamics, right, you actually deal with the heat of fusion. Okay, so we will try to connect it with heat of fusion. Now there is an equation, you know, that Gibbs-Helmholtz equation. Okay, which is basically says del of delta G by T, right? Of del T, okay, at constant pressure, of course. Okay, that is what? Minus delta H by RT square, right? That you know, right? So I'm just going to use that thing here. So if I'm going to use that thing, so basically I have to take derivative on both sides. Okay, let's do it. So I'm taking derivative of ln x. So it is nothing but d ln x1. Okay. You can write it, leave it like that, or you can proceed it. Okay, we'll see. Okay, so because here, yeah, we can just leave it as d ln x. And on right hand side, so what I'll have is d of this thing. Okay. So d of this thing, I can just write it as del t and kind of like this, right? Delta G by T. It was actually delta fusion G bar at constant pressure. Okay, and then I had 1 over R. That will be actually delta H by T, not T square. Okay, delta, it will be actually delta, the Gibbs-Helmholtz equation which I wrote, it will be minus delta H by T. Okay, not RT square, it will be T. Then we'll get the RT square from here. Okay. So, and there is a minus sign already. Okay. So, what we will have finally is, let me check the notation here. Yeah, that's fine. So, it will be basically, if I like it, it is 1 over RT square. Okay. And I have delta fusion H. Clear? Okay. Now we can actually integrate it. Okay. Integrate it basically from the two limits. Now d ln x already you know what it is. Okay, it is nothing but what? 1 over x1 dx1. On the left hand side I have written it something like this. Okay. Now we can integrate. Integrate to get what? Like if I have pure solvent, okay, then the corresponding temperature I am calling it as a Easter, okay, and if I have an arbitrary concentration, arbitrary mole fraction, then I am calling it as some arbitrary temperature. Clear? Okay, it's a straightforward integration. So the lower limit will be 0 here, as you can see. Right? So what we'll have, and we could have actually just integrated like this. Just keep it as d ln x. So the integrand is just ln x1, right? Yes.
Maybe t square only in the
Which one?
Let's say I have RT square, it is t square.
Okay, because that is already included, right? Okay. Here, and it will be R then, right? It will be T square then. I'm actually inserting that T, yeah, delta H by R with a minus sign. Yeah. Because actually, how you get it, the Gibbs rules is very easy, like it's a delta G, right? So you write it as a delta H minus T delta S, that way. Okay. And you will easily get it. Okay. Alright. Now, so we are all done basically. So what you see here is that dln x1, okay, minus 0. And the right hand side is basically 1 over t square integration. Okay, so it will be minus 1 over t, right? So let us just write it. So what we have is ln x1, okay, is, but there will be a minus sign because it is 1 over t square, right? So I can write it as delta function h. There was a bar sign because it's for 1 mole. Okay. And then I will have 1 over t minus 1 over t star. Okay. Assuming that during this integration, I am assuming that this is a constant, meaning the heat of fusion is constant over the range of temperature, which is not again a very like logical thing, but suppose for a small range, okay, we can assume that. Okay. Alright, so we got some relationship at this point. Okay. Now, usually, what happens is that when I talk about this mole fraction, okay, so what you do? It's basically mole fraction of the solvent, right? Now, mole fraction of the solvent, you usually, what you usually measure, okay, in lab, is that you take a solvent, okay, and you will add some salt, and you just tell how much salt is added per unit, say, gram, or per unit, say, like weight of the solvent, okay, which means that is somehow connected to the molality of the solution, because molality is a more useful quantity. Okay, now we can easily establish a relation between x, which is a mole fraction of the solvent, which is x1, with the molality. Okay, and we can make a generalized equation. Generalized equation in the sense I can actually develop a equation for a single solvent, which is a water, with multiple solids. Okay, let's say I added some salt as well as some sugar. Okay, after all, I mean at the end of the day, it doesn't matter because it will be the total molality of the solute, because everything is connected to only mole fraction, as I said. It really doesn't matter whether you added salt or sugar or together, right? Because these are all ideal solutions which we are discussing. Okay. Now, let us just try to find a relation between the molality of the solutes, okay, and the mole fraction of the solvent. Okay. Now, what is x1? x1 is a mole fraction, right? So the number of moles of solvent present, okay, divided by number of moles, the total number of moles, okay, into N3, N4. So 2, 3, 4 all are solutes. Clear? Okay. Now let us assume that the M is basically the molality. Molality means the total molality. Okay. And M is nothing but M1 plus M2, where M1 is basically molality of solute 1, M2 is molality of solute 2. Sorry, I should not write it as 1. We will start from 2, 3, 4, something like that. Okay. Because 2, 3, 4 are all for solutes, okay, and 1 I am keeping for solvent. Clear? Alright. And also assume that capital M, okay, is the molar mass of solvent. Let us write it as M1 because for solvent I am using 1. Okay. Alright. So then, just tell me what is then M2 by definition. M2 is basically the amount of solute 2, okay, per unit, like gram or something like that, right? So, which is basically I have N2, okay, divided by, I should have M times N1, okay. Similarly, I can write like N3 was also like this, N3 divided by m by n1. Here, this part is same because I am actually scaling it with respect to the solvent. Okay, because that's how you do the experiment. You have a fixed amount of solvent, okay, and then you add, okay, the solute, this much amount of solute I am adding, something like that. Okay, so I can easily see that I can actually write this by n2, okay, as something like I should write it as m1, m1 n1 into m1 n1 into m2. Similarly, M3 will be nothing but M1, N1, M3, something like that. Okay, so I can right now replace it. Okay, and as you can see, I will have N1. Anyway, these N1s will cancel because N2, N3, N4, okay, will all give me something like N1 plus M1, N1, that will be common. Okay. And then I'll have a summation of M2 plus M3 plus M4 and so on. Clear? Okay. But that I already took as small. Okay. So these N1s gets cancelled. Okay. So what I'll have is 1 divided by 1 plus capital M1 small. Okay. Clear? Yeah. Should I repeat once again?
So,
Yeah.
so modality is like moles of that given substance divided by the total amount. So
Yeah.
you're assuming here that the mass of the solute is negligible.
Why? No. Because it's basically the amount, right? It is the moles, right, of solute 2. It is solvent only.
So
Solvent is how much? N1 was from the beginning, right? And the molar mass of the solvent is M1. So how much solvent you have? M1 into N1.
right.
Okay. In a classic definition, usually people used to use like 100 gram. Like that is also kind of was there, but it doesn't matter. Like I can always scale it. But M1 into N1 is what? Like this is basically moles, right? And this is molar mass. Okay, gram per mole. So then what will be the amount? It is in grams, right? Grams of what? It is solvent, right? So for a fixed amount of solvent. So like what I'm saying is that you took 1 liter water. 1 liter water corresponds to say 1 gram per cc density if it has. Okay, it will have certain